Okay, so in today's lecture we are going to continue our discussion from last time where we were talking about the I/O subsystem, and today we are going to focus on the Minix subsystem, and we are going to look at both the device independent I/O subsystem code within Minix as well as the device drivers that are present in Minix and how they are implemented and so on. So what this slide shows us is the high-level layered architecture of the I/O subsystem in Minix. And as we can see, at the very lowest level, we actually have the hardware, which are the I/O devices in this case. The hardware typically interfaces with the rest of the machine through interrupts, and hence, as far as the lowest layer of Minix is concerned, within the kernel we have interrupt handlers, and those interrupt handlers interface with the device drivers as well as upper layers in the I/O subsystem software stack. Sitting above the interrupt handlers are the device drivers, and there's a device driver for each device. As we have seen last time, a device consists of the device itself and a device controller, and the device driver is responsible for interfacing with each device. So we have this device driver layer, and you have one driver per device that is going to be interfacing with the device itself. And the device driver includes all the device specific code, all the specific details of how to communicate with the device are encapsulated in each device driver. Sitting above the device drivers is the device independent OS code, and so this is code, as we will see, that deals with devices at a higher level of abstraction, such as block devices and character devices, as well as interfacing with user level software and so on. And then above this is the user level software itself. Now this picture, although we are discussing it in the context of Minix, is actually general, and any OS kernel will employ this architecture for interfacing with I/O devices. Now in the Minix specific context, some of this code that we see in this stack is actually part of the kernel. Some of it is in various system level tasks, including device drivers that we'll see are user level processes, the file system tasks, and so on. So we are going to see how this picture is realized in the Minix context by taking these various layers and putting them in different components within Minix. So as far as the highest level layer is concerned, which is the device independent layer, there are several different functions in it. As has been shown here, you need a uniform interface to communicate with all device drivers, because this code is independent of any device specific details. So it needs a standard interface to communicate with all of the device drivers, and it includes other functions that are common across device drivers, such as buffering, which we saw last time, is used to deal with mismatches between the device speeds and the CPU speeds. It includes error reporting or error handling, because I/O devices are slow and you're dealing with hardware, there could be errors, and then you got to decide how to deal with these errors. So some of that is encapsulated in this layer. And higher level tasks like allocating and releasing devices, deciding the size of the block that is used to communicate with the device driver, all of these functions are actually handled at the device independent layer. Now this picture is a cartoon picture, but it tries to illustrate how device drivers are built in two different contexts. One is where the OS does not have a standard interface, and one where there is. Now the first picture is supposed to illustrate how you can build device drivers even though the OS does not provide a standard interface. In this case, each device driver implements device specific code but exports its own interface to the rest of the OS, and the interface is one that makes the most sense for that device, including how you write to the device, how you write to the device, how you can send other kinds of commands to the device, and so on. Now, the Lego-like pieces, since they are of different shapes, what this is supposed to indicate to us is that the interface, in terms of how the device driver interfaces with the rest of the kernel, is different in case of each device driver, because each device driver is doing its own thing. It has its own interface that it has implemented. The figure on the right, which is labeled B, actually shows a different way of implementing device drivers. In this case, the OS kernel has standardized the interface for device drivers. So what that means is the OS has said, the kernel has said that all device drivers must support these functions that are used to communicate with it, and every device driver has to adhere to that standard. So there's a common way by which the rest of the OS actually interfaces with device drivers, and hence every device driver has to support exactly the same interface, and all of the details of how those interfaces are realized are inside the driver. So that interface, needless to say, must be general enough so that it supports a large class of devices regardless of the hardware details. In the first figure, each device driver could implement its own interface, which means that you could decide based on the type of the device what the interface should be, and some devices could have more functions in their interfaces and some less. In the figure B, every device driver supports exactly the same interface. In some sense, it has to be a union of what you need from all of the devices that you want to support in your system. Now, I should also say that most operating systems used to, in the old days, did not have a standard interface, so they looked more like the figure labeled A. But now, pretty much any general purpose OS has a standard way by which you implement a device driver, so they look more or less like B. So that is going to include Minix as well. Now, as far as the user space I/O is concerned, remember that Minix is a microkernel. So as we have seen in the past, and I'm going to show you again, many of the device drivers, not many, all of the device drivers actually are implemented as user space processes. Most of the kernel tasks are also implemented as user space processes and so on. So a lot of the I/O code actually resides outside the kernel. There is still some code that is inside, but a lot of it is outside. So it's instructive to see how a typical I/O request is handled in the context of using user space software and so on. So this is a layered picture that shows how requests from user processes are handled at different layers, and then all the way down to the hardware and all the responses. So at the top level, you have the user process itself. It could be any process that is trying to make an I/O request. Let's say, for simplicity, you're trying to read from a file. That's an I/O request. So the user process is going to issue the read request. That's going to come to some device independent software. In case of Minix, this is going to be a system process that typically is going to be a file system process which is going to basically handle your read request. And the device independent layer, in addition to interfacing with user processes, in case of Minix, is going to implement various features that I discussed 2 slides ago, which include things like naming and protection, deciding block sizes, implementing buffer caches, and so on. So this device independent software then takes the request and determines which device is supposed to handle it, and it hands it off to that right device driver. So remember that there will be more than one devices in your system. There could even be more than one disk in your system. In case of a read call, you have to decide which device that I/O request is going to be handled by, and you have to hand it to the specific device driver. So in this case, the device driver is responsible for implementing device specific code in terms of how that command, read command in this case, is going to be issued to that device and so on. It will have the ports that we had discussed last time that allow you to read or write data, have a status register, command registers, and so on. So the device driver is going to set up this device register and then maybe wait for an interrupt to come from the device when the request is done. So once the command has been issued, you just wait in the device driver, and then eventually there is going to be an interrupt from the device controller that tells the device driver the request is finished, and you see that the reply is now going to percolate up from the device driver back to the device independent software and back to the user process, where it is going to receive the results of its read command. So now let's look at some more details of how some of this is implemented in Minix. As I had mentioned, Minix device drivers run in user space, and you've seen this previously as well, because the kernel is bare bones. It implements a system task, a clock task, and some IPC. Everything else in Minix is actually handled in user space. So all device drivers run in user space. There's one process for each device driver. So each device driver is simply a user process. So what this also means is that device drivers cannot actually access either kernel memory or I/O ports. This is of course different from monolithic kernels, where the device drivers not only sit inside the kernel, they are the lowest level of the kernel and they are directly interfacing with the hardware. In this case, although that high level concept is true, device drivers are neither inside the kernel nor are the lowest layer of the kernel. They are sitting outside in user space, and yet they must somehow access all of the devices and do whatever a typical device driver does. So what this means is user space device drivers need a mechanism to communicate with their I/O devices, but all of that has to go through the kernel. So depending on what the device driver is trying to do, there will be different levels of access it might need. So for this slide actually talks about 4 different types of I/O accesses that a typical device driver might need. The first one is the device driver simply needs access to some memory that's outside its data space. This is not for interfacing with an I/O device. This may be for other reasons. So for example, we are soon going to see a Ramdisk driver where the data for this Ramdisk is stored in a different region of memory, and the device driver here will need access to that piece of memory. So that's the first kind of access. The second type of access is what a typical device driver does, which is the ability to read or write to I/O ports. And since I/O ports can be only accessed through the kernel, the code for accessing them even in Minix is in the kernel, and the device driver has to essentially use kernel calls to access these I/O ports. The third task that a device driver has to perform is handle interrupts. Typically in a monolithic kernel, when the device controller issues an interrupt, you essentially go into the interrupt handler, which is typically handled by the device driver. In this case, the device driver is a user process, so the hardware interrupt is actually going to come to the Minix kernel, not to the device driver, and the Minix kernel needs to be able to handle this interrupt by essentially forwarding it to a device driver. So all device drivers need to be able to handle interrupts, and here we are going to distinguish between predictable interrupts and unpredictable interrupts. Predictable interrupts are one that you know are going to arrive because you have, let's say, an I/O request outstanding. If you issued an I/O request, the device driver is going to wait for an I/O interrupt that will signal its completion. So that's, in our case, a predictable interrupt. Unpredictable interrupts are those that we don't know when they might occur. Examples might be network packets arriving on your Ethernet interface card. You don't know when communication is likely to occur. A packet might arrive at an arbitrary instant. Or a keyboard interrupt is also an unpredictable interrupt, because you don't know when the user might type the next keystroke. It may happen in a few seconds or few hours, and the OS is not, neither the OS nor the device driver actually knows when that is going to occur. So we will refer to these kinds of interrupts as unpredictable interrupts. Regardless of whether interrupts are predictable or unpredictable, they have to be handled by the device driver which sits in user space. And the way this is going to be done, as we will see shortly, is through messages that go between the kernel and device drivers. Now, having said that, all of the accesses that device drivers need from the kernel are actually implemented in the system task within the Minix microkernel. And let's look at each of these 4 types of I/O accesses in a little more detail. Okay. So the first one is where the device driver needs access to some region of memory that is outside its address space. And the example we gave here was one of a Ramdisk. So in this case, we are going to leverage a functionality of the system task. Because the system task is within the microkernel, it has the ability to access any process segments belonging to other processes accessible to a given process. So we are going to use that functionality to take, let's say, memory segments belonging to the Ramdisk, which is essentially going to be a piece of memory, and make it accessible to the Ramdisk driver. Normally you would not be able to do this because the Ramdisk driver is a user process that can only access its own stack and heap. It cannot access some other region of RAM, and in this case the Ramdisk resides outside the address space of the Ramdisk driver. So we are going to use the system task to make this possible. Another example where this is needed is where the console driver, or the graphics driver really, needs access to memory belonging to a video adapter or a GPU or a graphics card. So in this case, the graphics card memory is not going to be accessible directly to the driver, but the system task can take that piece of memory and make it accessible to the driver so that it can directly read or write to it, whereas you could normally not do that. So the second concept is where the Minix kernel has to provide access to I/O ports to device drivers, and typically I/O ports are going to be not accessible to drivers in user space. And again, we are going to leverage the system task that is going to perform I/O on behalf of the device driver, and we'll see how the hard disk driver is actually going to use it to perform I/O through the system task. The third thing that I spoke about in the previous slide is where you want to handle predictable interrupts. So here again we are going to leverage the system task. So the system task has a generic interrupt handler which is called the generic handler that it has instantiated. Any interrupt that comes in is handled by this generic interrupt handler, and it is then going to convert this interrupt into a message, specifically a notification message, and send it to the right device driver for handling. So interrupts essentially become messages. Messages are then sent to the drivers, and then each driver is essentially going to be sitting in a loop waiting for a message. So it's going to be doing a blocking receive call which waits for a message from, in this case, the system task, and when that message is sent to the driver, it's going to receive it and handle it. So this is how we are going to allow interrupts which arrive at the microkernel to essentially get forwarded to a device driver. And the last type of I/O access that a device driver needs are ones where you need to handle unpredictable interrupts. And because by definition interrupts within Minix or any other OS for that matter are unpredictable, you don't know how frequently they occur. You might have a second interrupt while the first one is still under process and so on. So, and furthermore, you don't even know the source of where the interrupt is coming from. It may come from any device, for example, an Ethernet card, a keyboard, a mouse, and so on. So the way you have to deal with this is slightly different from a predictable task or predictable interrupt. In a predictable interrupt, a device driver knows that the interrupt is going to come from a specific device because it has issued a command to that device. So it is expecting an interrupt to come from the device, so it can specifically do a receive for a message from that device. In the case of unpredictable interrupts, you don't know where the interrupt is coming from, so you cannot receive from a specific device because you don't even know which device is going to cause the interrupt. So you have to deal with this somewhat differently. So So you can do several things. First is that interrupt handling has to be fast, because the longer it takes, the other interrupts that are also unpredictable that arrive in the meantime may not get handled. So you want extremely fast interrupt handling. You want to do both non-blocking sends and non-blocking receives, because you can do it equivalent of things like polling or asynchronous receives, so that you don't actually block on a specific device. And a combination of these methods are actually used in the context of Minix to handle unpredictable interrupts. Now, this picture, with those concepts, this picture shows us again how device drivers are implemented both in a monolithic kernel and in Minix. So the picture to the right shows us a typical monolithic kernel. And you see the horizontal line is the one that divides the kernel space from user space. So everything above that line are user processes, everything below is the monolithic kernel. So the way the I/O works is user processes issue I/O requests, a file I/O request, or do something that triggers I/O. The request then comes down to the kernel. In this case, the file system is going to receive that request. It translates it into a read of a block. It hands that to the device driver. So that's how a device driver is going to then handle or receive that request and handle it. Now the picture to the left, labeled A, shows us how Minix device drivers work. And as I already mentioned, the only thing we have inside the kernel is a very bare bones microkernel, which has basic capabilities for handling things like interrupts and message passing and so on. As we can see, the device driver is a user process that sits outside the kernel. The file system is a user process or a system process that sits outside the kernel, and all user processes run outside as well. So in this case, when the user process issues a read call, it is going to arrive at the file system process. The file system process is going to hand that to the device driver to perform a disk read. The device driver is going to essentially issue a request to the disk controller through the system task, and then it's going to just wait for an interrupt to arrive. The system task at some later point is going to receive an interrupt from the disk controller saying that your read is completed, and that is going to be received. It's going to be turned into a notification message and sent off to the device driver. The device driver is expecting this interrupt, so it's sitting in a receive waiting for this interrupt. When the message is received, it's going to handle that interrupt, get the contents of the read, hand that to the system task, file system task, step 5, and then in step 6, which is where the read is finished from a system perspective, is the contents of the read are handed back to the user process. So you can see how an I/O request involves multiple components that are basically used to handle the request. Now, delving into a little more details of how Minix drivers work. As I already mentioned, each driver runs as a user-space process. For each type of device, there is a driver, because you need a driver for each I/O device, and each of them runs as a full-fledged user process. They communicate with the system task through message passing. And typically we'll see that simple drivers can be written in Minix in just a single file. And you will if you go to the drivers directory in the Minix GitHub, you will see that there are several folders. Each folder represents a device driver. I'm going to talk about some of them in this class, but I would encourage you to go and look at that the source tree for Minix and look at how some device drivers are written, and you will see that simple ones are maybe one file and some are maybe more than one, but by and large the simple ones are written in a single file, which means they are fairly simple and compact to write. Now, as far as the structure of each of these drivers is concerned, each of them has to accept requests from other processes. It could be the file system process, or the kernel system task, or something else, and carry out whatever request is actually being sent to them. All drivers in Minix are strictly sequential. They do not support concurrency to keep them simple. So some of the synchronization primitives that you might need in a multi-threaded kernels do not not required and in Minix. So it's much simpler to write a device driver, and by and large, as I said, they need to do three things. They need to receive a message, they need to process that message, and send a reply. Now each device driver it gets two types of request: a work request that comes from either the file server process or something else, and interrupts that come to the device driver from the kernel. So these are the two types of requests or messages that a drivers can receive, and you use the receive call to essentially receive interrupt messages as well as other kinds of messages. And while you are handling any request, whether it's interrupt or some other request, because this is single threaded and sequential, all other requests are going to arrive and just wait. So you're going to keep them pending, and this is especially true during interrupt handling, but also during processing of other requests. So it is essential that the processing of requests happen quickly, because there may be things like urgent interrupts that are come in, and if they have to wait for a while, that makes the system less responsive. So this slide just shows us some example types of messages that a device driver, a generic device driver, needs to handle. I'm not going to go through all of them, but I just want you to look at these, because the first table here shows us the type of request messages that are sent, and the second type shows us some of the reply messages. And you will see that typical fields of a message will include things like the type of the message, which is going to be the operation that was requested. There is essentially the device number that is basically used to address the device. I should mention here something that I should have mentioned earlier, that devices in Unix in general as well as Minix are going to be numbered. So each device has a number, and typically what you have are something called a major number and a minor number for each device. The major number for a device tells us the type of a device. So major number 1 could be disks, major number 2 could be graphics card, and 3 could be network cards, and so on. So those are classes of devices, and the minor number refers to a specific device within that class. So you might have major number 1, which is disk class, and minor number 1, which is disk 1 of the disk class, or device 1 of the disk class, and so on. So in this case, the device field that is shown here is actually the minor number, which is specifically addressing a certain type of device. You don't need the major number here, because the device driver already knows what type of device it is going to handle. So it needs to just know which device within that class to actually send that request to, or is that request meant for. And then you have other fields like what process request, that IO, the byte count, or the ioctal code, which I'm going to talk in a little bit, position of the device, and so on. And as far as reply is concerned, again you have the reply type, which is what kind of a reply it is. Typically in this case it's always going to be driver reply, saying this is a reply from the driver, and then it's going to talk about the process number and what bytes, the status that says what bytes, how many bytes were transferred, or the error number. Now this figure, rather the slide, shows us a typical pseudocode of a device driver, and you will see that all IO drivers essentially involve sitting in a loop, waiting for a request to arrive, and that is basically being done through the receive call, saying I can receive any message. And then once the message has been received, you essentially look at the type of the message, and then you handle it. So you could have a read message or write message or other kinds of messages. So you basically do whatever you need to do to handle those requests. In this case, if it's a read, you call a device read, which is where the code for actually reading from that device is implemented in the driver, and so on. And then once you're done, you basically send back a reply. That's the last line of that while loop, and then you continue and you wait and you accept the next request, and so on. So it's a strictly sequential while loop that implements a typical device driver in Minix. And what we are going to do is actually soon look at several types of device driver and try to understand how some of the code that is implemented by the device actually differs from device to device. So we'll specifically look at 3 or 4 different types of devices. There are 2 block devices and 2 character devices. So we'll look at, for as far as block devices are concerned, we'll look at the Ramdisk and hard disk driver. As far as character devices are concerned, we'll look at the terminal driver and keyboard driver. Now, recall that from the last class, I had mentioned that all devices are either going to be block devices or character devices. Block devices are those where the unit of I/O is essentially a block of data. And character devices are those where the unit of I/O is 1 character or 1 byte at a time. A keyboard is an example of a character device because each key press generates 1 byte that tells us what that key press is. Whereas a disk is an example of a block device because you are reading or writing entire blocks of data from the disk at a given time. So keep that distinction in mind because we are going to look at how Minix implements block devices as well as character devices, and we'll look at 4 examples in a little more detail. Now, before we get to whether there's a block device or a character device, let's start with a device independent layer. Now, in case of Minix, the designers decided that I/O's handling is closely tied to file system file handling because the disk is a very common device that is present in all machines, and the disk I/O certainly is very closely related to file I/O. So what they decided is all device independent code is going to sit within the file server process. Now, this is simply a design decision. There is no need to do this. You could have had a separate I/O process that did I/O handling and the file server process that just specifically looked at file system handling. But in this case, they put all of the code in the VFS process or the file server process. And we are going to look at the file server process in 2 classes from now. So that's something you want to keep in mind. And the VFS process implements the device independent layer. I showed you this picture earlier in the class where some generic handling of interrupts and so on is actually implemented. The handling of interrupts is done by the device driver, but the device independent code is implemented within the VFS layer, VFS process. So here is now a simple pseudocode for a block device driver, and you will see that this structure is not different from the pseudocode for a device driver that I showed you earlier. Clearly the pseudocode for the device driver is going to apply to both block devices and character devices, so the structure is by and large always going to be very similar. And here we have a generic pseudocode for a block device driver. Again, you see that there is an infinite while loop where you sit and you receive a message and then you look at whether it's a read or a write, and now you're going to essentially look for device specific or block specific reads and writes, and then you are going to call those messages. And what you see here are essentially function pointers. So in the case read, you see something that says star entry points pointer dev read. So that star entry is essentially a function pointer, which means that you can use this code to call different reads for different types of device driver because this is general. So you can essentially instantiate with functions for handling disk block drivers and other kinds of block drivers like graphics cards and so on. So this gives you a very generic structure to implement these various kinds of I/O requests. And then once you're done handling this, you are going to also just send back the reply through a send command. So what is also shown here, but as a comment, but without any code, is in addition to read write, of course, you have to do other things like open a device, close a device. We'll talk a little bit about I/O control or I/octals in just a little bit. So typical block devices need to handle 6 types of operations. So within that while loop that I showed you, in that switch statement, you will have to handle a read write, but you also need to handle open, close, I/O control, and scattered I/O. So I think the names of these message types indicate what the operation does. Open says you open a device for I/O. Just as you have to open a file for I/O, the device driver also has to open a device for I/O. Close tells you that you can close the device or done with the device. Read and write allow you to read or write to the device. IOCTLs or IOCTL, which are called IOCTLs or IO control, are messages that allow you to get and set parameters specific to the hardware. So for example, you might have things like transmission speed to the device, the parity of the device. In some cases, you might be able to set the chunk of data that you use to read or write to the device. So some of these parameters can be controlled through software, and the command that is used within Unix in general as well as Minix is called IOCTLs or IO control. So that is implemented by every device driver to allow you to change device specific characteristics that you might need to control after boot time at runtime. When the last operation is called scattered IO, and this is basically an operation that is part of a general concept called scatter gather IO. Now in scatter gather IO, what happens is you are trying to read multiple blocks or write multiple blocks at a time. So so what happens is, rather than reading or writing one block at a time, you issue concurrent requests, read requests, say. So you basically scatter them out. They go off to the device, let's say the disk, and the disk performs concurrent reads, and then you gather all of the responses and you construct one reply message and send it out. So this is called scatter gather. So you allow, it's essentially one way to think of this is batched IO. You batch multiple requests and you send them out because they're random, they scatter, meaning they go to different locations on a disk in case of a disk, or if you're trying to write to different parts of a screen, they will scatter to different portions in a graphics card. And then in case of a disk, at least you have the gather operation where the replies come back and you essentially gather all of the requests and so on. So devices such as disks are going to implement this operation for more efficient IO. You can basically batch these requests and get higher throughput. So this is going to be an addition to the read and write, which allow you to read one block at a time or write one block at a time. So with that concept, now let's look at some specific block device drivers. We'll start with a simple one called a RAM disk. A RAM disk is very similar to a hard disk, except that the contents of this disk sit in memory. Okay. Now clearly memory is a volatile device, so you cannot actually use it for long-term persistent storage of files. So you're going to use RAM disk as a temporary storage region, but this portion of memory essentially looks like a disk rather than memory. Okay, now what's the difference between a disk and memory? In case of RAM, you can address individual words in RAM. So you give a memory address in terms of a pointer and you can go address that specific memory region. Now disks are block devices, which means that the granularity of IO is one block. You cannot access one word or one byte within the block. The IO operation says you read the entire block or write an entire block. So when a region of memory is being used as a RAM disk, you can think of IO being done in terms of blocks or essentially pages or something like that, where you can only the RAM disk driver allows you to read or write entire blocks, not portions of a block at a time. So that's something you want to keep in mind. So now, why do we need RAM disks? Typically, most of your files are actually going to be stored on a persistent storage device, such as an actual hard disk. Right? But RAM disks are especially useful when you are booting your machine. So before you have access to the hard disk, you can construct a temporary RAM disk. You can load the boot image, which is the kernel part of the boot image or other things within the boot image, into the RAM disk. So now that portion of memory looks like a user process. It looks like a hard disk, and you can then access that hard disk through the RAM disk as if you are reading or writing files to the local disk. So that's the concept of a RAM disk, and it is used by most Unix-like operating systems for access to files during the boot process before the actual hard disk becomes available. So you basically bootstrap the OS through a small RAM disk, then you access the hard disk, and then you can load the remaining files on the hard disk and so on. So now as far as the RAM disk driver is concerned, the typical block driver is going to read or write a block. So the RAM disk is going to essentially have a pre-allocated region of memory where you can read or write these blocks, and then there's a file system that is going to be running on top of that RAM disk. Now the Minix RAM disk driver actually uses 6 much more simpler drivers to implement RAM disk functionality, and those are listed in this slide. And each of them looks like a device. So if you remember what I said last time, you basically access devices through a file name and a file system interface. All devices are essentially present in the /dev directory within Minix or even in Unix, and the name of a file tells you what kind of device it is. And we have 6 different devices that are accessed through the /dev interface and that implement the RAM disk functionality. So /dev/RAM is the actual RAM disk. So that device is going to essentially, when you try to read or write to that device, it looks like a file because it looks as a file name. And that quote-unquote file essentially points to a RAM disk in memory. So you can basically go and read or write blocks from that RAM disk. /dev/memory is a device that essentially allows you to access physical memory by addressing it. Now, this is essentially only accessible to the kernel, and the kernel can use this interface to actually read or write to specific regions of memory. The RAM disk driver is also going to use this device. /dev/kmem, as you can imagine, is essentially a device that refers to kernel memory. So this is the part of RAM where the kernel resides, and that entire region of the kernel address space is exposed to the RAM disk driver through a device called /dev/kmem. So in this case, byte off, so again it looks like a file, the entire region of memory, although it's not really a file, it's just a region of memory, and you can offset any byte and that points you to a specific region of kernel memory. /dev/boot is a device that is used during boot time. It holds the boot image, and you have 2 other devices, /dev/null, which is an output device that allows you to write to an output, and the output is discarded, and /dev/0, which is an input device. Basically, if you try to read from the device, it's going to only allow you to read a 0 every time. So typically it's used to zero out regions of memory. Okay. So the code for the RAM disk driver is in the drivers folder in the Minix subtree, and you can see it under the RAM disk and the memory folder. It's scattered between those two because, as I said, the RAM disk driver uses 6 different devices to implement its functionality. Okay. So the next driver that we are going to talk about is the hard disk driver. Typically you have different types of hard disks. The old style has been magnetic hard disks, which are spinning disks. They look like CD-ROMs. They are circular platters that spin, and you have data that's written to them in terms of cylinders, which are essentially platters. Each cylinder essentially has concentric circles that are called track. You write data on the track, and each track is divided into sectors. We are going to look at disks again in the next class, and I'm going to show you some pictures that illustrate how this is done. But for the purposes of this class, all we need to know is the hard disk driver takes the disk geometry, which is cylinder, track, and sector, and disk addresses, which are essentially going to refer to a cylinder number, a track on that cylinder, and a sector, and just turn that into a linear addressable space, which is called logical block addressing. So essentially you can take all the sectors on the disk, it doesn't matter what geometry they are in, and you can just number them 0 through n, and now you can just access them as sector 0 and sector 1 and sector 2 and so on. Those are logical addresses, and they can simply be translated within the device driver to physical addresses, which are each logical block number essentially becomes a sector, a track, and a cylinder number. So that mapping can be done internally. So devices, the hard disks can be accessed either through a logical block address or through a physical block address. Now, within Minix, the code for the hard disk driver is in the AT/WINIVINI folder, and that essentially refers to Winchester drives, because another name for hard disks in the old days used to be Winchester drives, and that is where the code is stored. And the thing I do want to mention is, from a hardware perspective, you can actually have more than one disks connected to your machine. So you can have more than one IDE disks or more than one SATA disk. SATA is just an acronym that stands for Serial AT Attachment. It's a hardware standard that allows you to essentially interface with the disk. So you can have up to 4 disks, and to figure out which disk you're reading or writing to, as I said, you're going to have a major number and a minor number. So /dev/C0D0 is going to refer to the first number. C0 refers to the class called disk, and D0 says disk 0 within that class, and D1 will say disk 1 if you're more than one in your machine. So I would encourage you to actually go into your Minix VirtualBox VM and type the df command, and you will see a whole bunch of devices that are mounted, and you will see things like /dev/D0, which is the disk, and you might see additional suffixes there which say that's a partition within that disk that get mounted as the root directory, and so on and so forth. Now, the disk driver has to interface with the disk controller, and the way you're going to do this is the controller will essentially have ports, as we mentioned last time. Each device has a port, so you'll have control register, which is a control port where you can essentially send commands. And the table here shows us the different types of register values you can write and what they mean. So you can essentially have multiple registers in the control register, not just one in the case of the IDE hard disk. And you can essentially say, I want to do a read or I want to do a write, and you can specify the address either in the LBA mode, which means it's a logical address, or you can specify them as a cylinder, track, and a sector, which is a physical address. You can address either way. Typically, you would like to do it logical, and then the controller can do a translation for you. So again, this slide essentially shows us the fields of the drive and head register, which basically again which tells us how you're actually doing the addressing. The device driver has to read or write registers here, or in this case write register to these values that specify addresses of what you're going to read or write. Okay, so again you can use the LBA mode. If the LBA field is 0, you're essentially using the cylinder head sector mode. If it's 1, you're using the LBS driver. So I'm going to now quickly move on to two other types of devices, which are terminals and keyboard. So typically they are character devices, but we'll see that terminals don't have to be. They can be block or character based. So what this figure shows is the various kinds of terminals. A terminal is a generic concept within Unix that refers to all kinds of monitors where you can actually see output from your machine. And then there are different kinds of monitors that have evolved over the ages, and you will basically see that some of them are memory mapped interfaces, some of them use serial RS-232 interfaces, still others use network interfaces. Monitors or terminals can come in many different flavors depending on whether they are connected to your graphics card, in which case they become memory mapped terminals. Whether they are using a simple RS-32 serial interface, these are the old style terminals where you can simply see a character console but nothing more, that uses an RS-232 interface. Or you can actually use an actual network to communicate with the remote terminal, in this case X terminal, where the communication to the terminal actually goes over a network. And so terminal drivers, as you can imagine, are quite complex depending on what type of terminal it is, how you are communicating with that terminal, and so on. Right? So let's go into this in a little more detail. So this figure here shows us memory map terminals. So this is the standard kind of monitor that you will see today, where you have a graphics card or a graphics adapter, and you connected a monitor to that graphics card. Okay, so keep in mind here that the input and output are different. The input is coming from a keyboard, so there's a keyboard driver that's separate, and then the output is going to a graphics card, and the graphics card is displaying that output onto a monitor. So you will see that the graphics card essentially has some video memory that's separate from physical memory. Okay, so the video RAM or the graphics RAM is separate from physical memory, and typically to output something to a monitor, you have to write to that video memory, and based on what you have written, the graphics controller is essentially going to take that content and display it at the right location or on the monitor. Okay, so when typically these are memory mapped. What that, if you remember what I mentioned last time, a memory mapped I/O essentially means that you take the device memory and you make it as part of physical RAM. So in this case, video RAM just becomes an extension to physical RAM. So you can think of physical actual RAM and video RAM, and you concatenate the two, so you have one larger address space. And so some addresses, when you write to those addresses, you write to video RAM, and some addresses when you write to them or read from them, you basically address physical RAM. So you're using memory mapped I/O, which makes it very simple to write to a graphics card. You just write to a specific address, and then the graphics controller simply outputs whatever you written to the screen. So here is an example of a very simple character display. Displays come in two types. One is character and one is bitmap. Character display simply show you, it's like a console or X terminal, it simply shows you character. So in this case, you're not outputting pixels, you're outputting character. So you can write A to the screen and it's going to display A and so. So what happens is you take your screen, and essentially you have a screen that is in this case shown in figure to your right. It has 25 characters, 25 lines by 80 characters. So you can output the number of characters you can output is 80 by 25. So you can think of that as an array. Okay? So your video RAM is going to essentially mirror what is the screen. So there's an array in video RAM, and you can essentially write a character to think of this as a two-dimensional array. So if you write a specific character to a specific region of that array, that character is going to be displayed at that location on the screen. So there is a one-to-one mapping between the two-dimensional array that is represented by the video RAM and what is actually represented on the screen. So to output something on the screen, you're simply going to write to a specific region of this video RAM, a specific location of this two-dimensional array in the video RAM, and the corresponding character is going to be shown. So what is shown here, as you can see, is at the bottom you have essentially written A, B, C, D, and then A, B, C, D appears on the screen. And the mapping here is from the lowest line of the video RAM is the top line of the screen, but ignore that for a moment. So you can write to any region and that character is going to appear. So that's how you can work with character displays. Now you have other kinds of displays are bitmap. So those are the displays we have on our laptops, on our phones, and on our desktops. So here, rather than writing characters, the screen is essentially a set of pixels, right? And so each pixel can be written to individually. So you can essentially decide the color of the pixel, and so on. And then you have a video RAM where so again it's a two-dimensional array, but each entry is now a pixel as opposed to a character. So you can address each pixel individually by writing a value to that pixel, and that value is a color code. Right? So you can say the color code specifies what color the pixel is going to display on the screen. So simply by writing to that video RAM, you can essentially change the color of any pixel and so on the screen. So those are memory mapped terminals. You also have character terminals, or rather RS-232 terminals, where these are character terminals, but you are not using a graphics adapter, you're using a serial interface. So as is shown in this picture, the terminal actually in this case is the one shown to the right. It has both a display and a keyboard. So it is basically both an input and an output device, and you have a serial cable that is connected from your computer to the terminal. The serial cable allows two-way communication. It allows you to send characters to the screen. It also allows you to read keyboard input from the keyboard and read it here. So So you have a RS-232 driver that is basically going to take whatever characters you're writing, converts it into serial command, sends it over the serial interface. The serial commands are basically using a protocol called UART, which we really don't need to go into, but UART allows you to do serial communication. So it allows you to both transmit and receive to the terminal. Now these are no longer used in practice, but there are some special cases, embedded systems and so on, where they're still used, but you will not see RS-232 terminals connected to a laptop or a PC. But there's when you go to embedded devices and things of that sort, you might still use RS-232 for communicating with the terminal. Now, the way these terminals work is essentially you have a buffer pool, which is like a circular buffer where you can read or write. So keyboard input arrives and it essentially sits in a circular pool, and then the device driver in this case is going to keep reading those characters and then processing them and so on. And to write also, you have this kind of buffer that is being used to output to the terminal. Okay. Now, very quickly, the terminal driver has to, in this case, do a few different things. You can read from the terminal. Again, the read commands essentially arrive to the VFS server and then on behalf of a user process, and then are handled by the device driver. The read only is true if you are using an RS-232 terminal. If you have a standard graphics card with a monitor, you are not going to be reading from it, except that more modern monitors might have a touch screen, in which case they become both input and output. But in only the older RS-232 terminals actually have a keyboard that is part of the terminal device, but not more modern screens except for a touch screen. You can of course write to the terminal, which is your outputting characters or pixels to the terminal, or you can essentially use ioctl commands which allow you to set terminal parameters, how frequently do you want to communicate. In case of the graphics card, this is maybe the frequency of output. Are you doing 30 Hz or 60 Hz, or are you changing the resolution and so on. So these are all done through the ioctl command. You also need to handle certain other types of messages, such as there was an IO from the screen, which could be a keyboard interrupt. You might have to also do things like standard things like opening and closing devices and so on. Okay. So all of that is shown in this picture here, where your user process that is trying to read from a terminal. Let's say it's a touch screen, you want to see if there's been some touch input. You basically, since the device is exposed as a file, you essentially handle it through the file server process. So you read from the file server process, that sends it to the TTY driver. In this case, that's a terminal driver. The terminal driver is going to wait for a receive from the system task. Whenever there's a keyboard input that generates an interrupt, it goes to the system task. The system task makes a notification message, sends it to the terminal driver. That's step 4, and then the terminal driver is going to essentially read from the buffer and then decide what it needs to do, and then finally hand that input to the user process for handling. The output is very similar. You have a terminal task, it's going to do a write, it's going to go through some event handler and then output characters to the screen, and then you flush to the screen. And remember that higher level concept is if it is a memory mapped device, you have a video RAM where you're essentially writing this output to. The video RAM essentially uses the graphics card controller to output that to your screen. Okay. And the last driver I want to talk about very briefly is the keyboard driver. And typically on most machines, the keyboard driver is separate from the terminal driver. Except in RS-232, they are part of the same device. But typically the keyboard could be a USB keyboard and the graphics card is separate. So the keyboard driver is actually very simple. Every time you press a key on your keyboard, it generates an integer code gets generated that represents what key has been pressed. So for every key on your keyboard, there's an integer code. So A key would have a code, and the B key would have a code, and the function key would have a code, and so on. And some of that mapping is actually shown in this figure here. So every time you press a key, it generates a code. That code goes and sits in a small buffer, and the keyboard generates an interrupt. The keyboard driver is then going to have to go and read that keyboard input from the keyboard buffer and then hand it to whatever process was actually receiving that input at the current time. At any time, there's some process that is designated as active, and that's the one that's going to receive that input. Now, I should also mention that because you can press these keys on your keyboard very rapidly, there's a small buffer on your keyboard which will buffer this. And this is done because the keyboard driver may not be able to process inputs as quickly as you press them. Sometimes if you hold a key and press it down, it generates rapid amount of input, and typically you may not be able to handle it, so you buffer them and then you wait for the keyboard driver to receive them one character at a time, because it is going to be doing one character at a time processing. So again, I would encourage you to go and look at some of these drivers in the source code tree of Minix. Some of them are very simple, some of them are a little more complicated. The device drivers are in the drivers directory. Some of the other code, which is the device independent code, you have to go into the VFS system process and look in the file server process. And as part of the final project, you will have to implement a very simple device driver, so it's instructive to go and understand how all of this works. So with that, I'm going to end this today. Tomorrow, and then in the next class, we are going to switch to file systems and file server process within Minix and so on, which will be the last big component of this course.